Okay, so I want to talk today about only a few specific theorems because the subject of Riemannian geometry itself is vast and there are lots of great and beautiful theorems which one would like to talk about for hours and end. But I'd like to focus on a few specific theorems which will fit well with whatever you have seen in the course. Okay? So it's definitely not a comprehensive list of theorems. There cannot be such a list in a 1 hour talk. But we'll try to highlight how geometry influences topology, how it interacts with topology, and how curvature imposes certain restrictions on the shape of manifolds. Okay, so this is more of an overview talk where I'll be mentioning theorems along with people who have proved them, some history, but almost no proof, and some of the proofs will be either covered by the presentation, some of the proofs are in the textbooks, while some of the proofs are almost cutting edge research. So this is more to inspire all of you to go back and read up more on these things if that is something that you like. Okay. So yeah, so having said that, let's start. So it's a brief tour of a few important results, only a handful of them. And I've chosen them specifically so that it resonates well with whatever you have learned in this 4.5 months or so. Okay? 5 months now. So we'll broadly divide this into 4 sections. The first one is going to be on completeness. And the canonical theorem that comes to mind when one talks of completeness is the Hopf-Reno theorem, which was proved around 1931. This is actually going to be presented to you, I think, in almost the same but slightly different ways by Rahul Mondal on one hand and then Aruni Pal on the other hand. So if you attend their presentations, you'll see how one proves such a thing. I'll get into the details of these in a moment. Let me just give you the breakup. So we want to talk about completeness, and the first theorem that you want to talk about is Hopf-Reno theorem. We had talked about this a little bit in the class when we talked about geodesic spaces and metric spaces. The second theorem, which is not really a completeness result, but it hinges crucially on the Hopf-Reno theorem. So I've put it in this box, is the Hadamard-Cartan theorem. And the reason why there are 2 dates and is because Hadamard had proved this theorem for surfaces in 1898, and then Cartan generalized this to all Riemannian manifolds in 1928. So that's why I've written them in non-alphabetical order, although alphabetical order is usually the way to write things, simply because it's easier to read off the dates. Okay, okay, so the next we want to talk about are results regarding constant curvature Riemannian manifolds. And here and in subsequent slides, when we talk about constant curvature, we mean constant sectional curvature, okay? Not constant Ricci, not constant scalar, constant sectional curvature. So regarding constant curvature, there are a few projects that are lined up. So I think Shandip is going to talk about how Riemann surfaces can be equipped with a metric of constant negative curvature -1. I think Pallav is going to talk about what are the isometries of the hyperbolic plane, which has constant negative curvature. But these are only for dimension 2. In general, you can ask for a classification of constant sectional curvature in higher dimensions. And that's what this theorem by Killing and Hoff talks about. Okay? And again, these are 2 dates because they were sort of proved separately and independently, and one proved a version of, and then the other one generalized it to the whole setting. So that's by Killing and Hoff, 1891 and 1926. So we are starting way back in 1891. So that's almost 130 years back, right? Okay, and there are dates in the middle. The next topic we want to touch upon is the topic of fundamental groups. And there's actually a whole lot one can talk about here. It's just a huge box that I don't want to open. Well, for the simple reason that I am definitely not an expert on this, but there's way too much material here and big people have worked on this. But we want to state this theorem by Priceman. And this is a theorem which is stated and proved in Docarmo. So if you want to read up, you can do that. So this is a theorem which talks about what kind of fundamental groups can appear as the fundamental group of a manifold if you put curvature restrictions. meaning if you put restrictions on the sectional curvature. Okay, and then there's a result of Cartan, which is about the fundamental proof, but it doesn't quite impose curvature restrictions, and we'll talk about that. Unfortunately I couldn't dig up the date on this, but there's a date somewhere in the middle. And then there's this theorem by Lusternik and Fett, which is a very beautiful theorem, and it has led to a whole bunch of deep mathematics afterwards. And I want to talk about that a bit. So this was in 1951. So the last two statements by Cartan and Lusternik and Fett, they all try to find closed geodesics. So we've all talked about geodesics quite a bit, but you're looking for a closed geodesic, meaning you're looking for a loop, which is a geodesic, not a curve. Okay? So that's what these two theorems address. And this goes into quite deep and fascinating mathematics. It goes into dynamical systems, it goes into Morse theory, it goes into differential geometry, calculus of variations, all sorts of things you can think of, it goes in there. So anyway, that's the rich history behind this. And the last topic that I want to talk about is the topic of sphere theorems. And I'll not say much about this. We'll see what it is when we get there. So the first theorem is by Berger and Klingenberg, built upon other people's work. This is in 1960. And then this was extended to the smooth setting by Simon Brendel and Rick Shane in 2007, okay, which is quite recent in mathematical terms. So you have the whole spectrum starting with 1891 and ending in 2007. Okay. And we'll see somewhere in one of these sections, Ricci flow is going to appear. So you should remember Ricci flow from the last talk, where we talked about Ricci curvature, Ricci flow, and how Ricci flow was used by Perelman to prove the Poincare conjecture. So that's going to make an appearance at some point. Okay. So that's basically the setup. So we're going to talk about these 4 topics and the relevant theorems there. So any questions so far? Or comments? So by the way, one thing is, if you wanted to really read some of these theorems, so Hoff-Rino and Hadamard-Cartan's theorem, they will be presented, but they're there in Docarmo, for instance, or any reasonable Riemannian geometry text. The Killinghoff is also there in Docarmo. Preissmann's theorem and Cartan's theorem is there in Docarmo. The Lusternik-Fett is not quite there, but I would suggest other references for Lusternik-Fett, and I'll mention them when we get there. The Berger-Klingenberg is probably sketched in Docarmo. I'm not sure if he entirely proves everything in details. And Brendel Shane, as far as I know, was originally a paper, and then they wrote a note on it. But I don't know if there's a textbook which proves this theorem. Maybe it does by now, but I'm not aware of the literature very much on this topic. Okay? So that's the references if you want to look these up. Okay. So let's see. I guess just a second. Okay. So recall that if I have a Riemannian manifold, M comma G, G is the Riemannian metric, then it induces an actual metric D on M. So an actual metric D is simply a function from M cross M to R, such that it's non-negative, it satisfies reflexivity, that D of xy is 0 if and only if x is equal to y, satisfies symmetry, and it satisfies triangle inequality. So this metric D is induced by the length function, because you know how to compute lengths of piecewise smooth curves, and then you take the infimum of paths joining P to Q, you declare that to be distance between P to Q. Okay, and we have also seen that the topology induced by this metric D is nothing but the old topology on M that you start off with. So you're not creating a new topology by choosing a Riemannian metric and inducing a metric D. You get the same topology back. Okay, so actually now that you know normal neighborhoods and exponential map is a diffeomorphism and so on, is a local diffeomorphism, I think there's an easy proof that the topology induced by D and the original topology of M are equivalent, simply because you can use normal neighborhoods. Okay, so that's the usual proof that you see in Riemannian geometry books. But that proof comes at the cost that you have to do it only after you've introduced exponential neighborhoods. Okay. Anyway, so this is something we have seen. So here's the famous theorem of Hoff and Rino. So this is Heinz Hoff and Reno. So let M be a connected Riemannian manifold and let P be a point in M. So there are several versions of half Reno. They're more or less equivalent. This is the version which is there in Ducarmo, for instance. Okay? So then there will be 4 assertions, A, B, C, D, and all the 4 are equivalent. So what is the first assertion? That you look at the exponential map X at P. The claim is that the exponential map is defined on TPM. That's the first assertion, sorry, not claim. So typically the exponential map is only defined on a small neighbor of the origin in TPM, but you're assuming that the exponential map is defined on the whole tangent plane, which simply means that if you have a geodesic with some initial velocity at P, then the geodesic exists for all times backward and forward. That's what this means, okay? Condition B says that closed and bounded sets are compact, okay? That's a very nice condition to have and should remind you of Henneborel theorem for all you sort of care. And the third condition is a condition about completeness of metric spaces. It's saying that consider M as a metric space now that you have a metric D which induces a topology. The D comes from a choice of a Riemannian metric G. Okay, and so this is saying that M is complete as a metric space. So M comma D is a complete metric space, meaning all quotient sequences converge. And the last condition is M is geodesically complete. So what does geodesically complete mean? Recall that geodesically complete simply means that we know that geodesics exist for small times, simply because you can solve the set of differential equations locally. So geodesically complete means that if I give you an initial point and an initial velocity, that geodesic exists for all times. Okay, and this is for any initial data. So that's what geodesically complete means. Okay, that any geodesic can be extended for all times. Okay, so in the last 3 conditions, there is no dependence on P. The first condition, of course, depends on the P that you chose. Okay? So the theorem says that A, B, C, D are all equivalent. And you can think about a proof of this if you are really curious, or you can read Ducarmo, or even better still, you should hear what Oroni or Rahul has to say about this, and then I mean, hopefully they will, in time, they will be the local experts on this theorem. Okay, so it turns out that any one of these 4 equivalent conditions actually implies something nice. It says that given any 2 points P and Q, there is a minimal geodesic gamma. Yes, any questions? I thought I heard some voice. Okay, fine. If there are any questions, just feel free to ask. Okay. So any of these above equivalent 4 conditions implies that if I give you any 2 points P and Q, there is a minimal geodesic gamma joining P and Q, which means what? Which means there's a, first of all, gamma is a geodesic. Secondly, gamma joins P to Q. And minimal means that the length of gamma is actually the distance between the 2 points. That's what minimal means. Okay? And the picture that you should have in mind is if I give you the North Pole and the South Pole on the sphere, any of the half longitudes will join the North Pole to the South Pole. But you could basically go once full around the South Pole and then go back. That's also a geodesic, right? But that's not minimal because the length along that curve will be 6 pi, but the usual length is like 3 pi, the usual length is pi. So minimal means it realizes the distance. Okay? So there is a minimal geodesic because typically there could be more than one minimal geodesics joining 2 points, but there is at least one. That's what any of the 4 conditions imply. Okay, and
sir,
yes.
Sir, can you give an example of a manifold where the exponential map cannot be defined?
Yeah, plenty of them. So now, according to this theorem, just choose any manifold which is not complete. So, for example, take R2 minus 0, the origin, right, with the usual metric. So the exponential map is simply going to be straight lines, right? I mean, because,
Yes.
and so if you start at the point 1, 0, and if you look at the exponential map with P equal to 1, 0, the exponential map is simply going to take a vector at 1, 0, and it's going to be the radial line in that direction initialized at the point 1, 0. But if you take the vector which is pointing towards the x-axis on the negative side, that radial line is basically a line going from 1, 0 to the left. But that cannot be defined for all times, right? Because it has to go through 0, 0.
But we can, okay, yes.
So it is only typically the exponential map is only defined on a small ball or a small set. That's because the exponential, the geodesic will not exist. So here it doesn't exist because there's a gap, but you can cook up a lot of other things in the same way. So we had seen another example that you take the stereographic projection, take S2 minus a point, take S2 minus the north pole, stereographically project onto R2, and you get a metric on R2. And we did this example in class, and that metric is not complete. And when you calculate the exponential map there, you see that the exponential map cannot be extended beyond pi over 2. It's not because you know like there's a gap in the space, because R2 there's no gap, but on at pi over 2 itself you reach the end of R2, so to speak. So you cannot go beyond pi over 2 in that example. So you can use this theorem to cook up examples, for instance. So does that answer your question?
Actually, I wanted to ask this question because I wanted to think other way around. Uh, like here you use the fact that like you took a example of a metric space which is not complete, and then you using in that metric space you gave a counter example.
Yeah, but
So
I'm
I
saying
want,
no, but I'm saying that's just the way
yeah,
I.
yeah, I got your point.
But I could have just not mentioned that it's complete and said that look at R2 minus 0 and look at these exponential map. The exponential
Hmm.
map really looks like radial lines emanating from a point, and radial lines cannot exist for lines which go through the origin, right?
Hmm.
So for that reason only the exponential map will not be defined, and any of the
Yeah,
other things are not true, right? So in some examples, like I said, I gave you the stereographic example where completeness is not immediate, but it's kind of obvious. You take the induced metric on R2, which comes from the stereographic projection of S2 minus the north pole. And that turns out to be not a complete metric space. But if you, even if you didn't know that, if you really calculated the geodesics, and we did that in class, the geodesics, a typical geodesic can only be extended up to pi over 2, and it cannot be extended beyond pi over 2. And that's not because that there are some gaps in R2, because clearly there aren't, right? But that's simply because at pi over 2 any unit speed geodesic reaches the end of R2, so it basically goes to infinity in whatever direction, so you have no place to go after that. So that's the other kind of phenomena, if that helps your thinking, which can happen.
Hmm.
So yeah, but now with this theorem, the point is that these are so intrinsically related to each other that to construct a counterexample, you basically have to construct a counterexample violating whichever of the four conditions is useful in that context. So if closed and bounded sets, some closed bounded are not compact, then you can use that too if you want, but that is probably not a good thing to use to construct. But C is very useful to construct counterexamples. So yeah, so okay, any other questions? Okay, so actually if you recall, we had talked about a metric space version of this in the class, and that is also true, but that is due to two other people. But anyway, so the point is that one of the key things that you can take home from the Hoff-Rino theorem is that the notion of geodesic completeness, which is a more geometric notion of completeness, coincides with the usual metric space notion of completeness, right? Cauchy sequences converge. So these two are one and the same. That's what Hoff-Rino is saying. So it's a classical and very nice theorem, and we'll see a proof of this in a couple of weeks. Okay, good. So actually in Docarmo there's another equivalent condition E regarding an exhaustion of M by compact sets, but I left that out because I think anyway this is probably the more commonplace version. Okay, so let's move on to this other theorem which we talked about, called the Hadamard-Cartan theorem, which is called the Hadamard theorem in Docarmo's book, but Hadamard proved it for surfaces and Cartan generalized it almost, I think, 39 years later. So it requires an analysis of Jacobi fields, which I'll not talk about because we didn't have time to talk about this in this course in any case. So there's a very crucial technique that is used where you basically try to play around with one parameter family of geodesics varying through geodesics and calculate various derivatives and develop a theory. That's what Jacobi fields are. So you have a one parameter family of geodesics and you look at their the derivatives and see what kind of equations they satisfy. So that's a whole analysis on its own, where you have to combine that analysis with the Hopf-Reno theorem to obtain this following result. Okay? And this is a very, very beautiful result. I mean, I will like it simply because the statement is so nice, simple, and beautiful. So let Mn be a complete Riemannian manifold, which is simply connected. N stands for the dimension of M, and I hope all of you remember that simply connected means that it's a connected space which has fundamental group 0. Okay, or a path connected space in this case, because M is locally path connected, so connected and path connected are the same. So simply connected means that the fundamental group is 0, which simply means that if I take any loop based at a point P, then that loop is contractible, fixing base point. So any loop is homotopic to the constant loop at the base point, right? That's what this means. So if you have such a manifold, then you're going to impose certain curvature restrictions on there. If you don't impose any curvature restrictions, you cannot say anything nice, because there are plenty of simply connected Riemannian manifolds which are complete. If you impose the condition that the sectional curvatures are all non-positive, okay, meaning that take any point P, take any two-plane sigma in TPM, look at the sectional curvature associated to sigma at the point P, and that is less than or equal to 0. Okay, for any P and any sigma. So if the sectional curvature is bounded above by 0, then the exponential map at any point P, so this P is arbitrary, the exponential P from TPM to M is a diffeomorphism. So the first thing is that you might ask, why is the exponential map defined on all of TPM? Well, that's because we're assuming that M is complete. But complete as a metric space is equivalent to geodesic completeness, which means the exponential map at any point P is defined on all of TPM. Hence, this map makes sense. That's essentially Hopf-Reno. And then you have to somehow analyze what non-positive sectional curvature buys you to claim that this map is a diffeomorphism. So all we know so far is that the exponential map at P is usually not defined everywhere. Even if it's defined on TPM, it's a local diffeomorphism at the origin. That's the crucial thing, right? But they're saying it's a diffeomorphism on its own, which means M is diffeomorphic to TPM, but TPM is basically Rn, so M is diffeomorphic to Rn. So that's a very beautiful result, right? Okay, so let me make a few comments on this. So the key sort of step, and you'll see this in, I believe, Arantha's presentation. A key step is, so she's not going to talk about Jacobi fields, but she's going to assume the relevant results that Jacobi field gives you. But the crucial step is this, that if you assume that your manifold has non-positive sectional curvature, then that implies something more than what we know. It implies that the exponential map is a local diffeomorphism for any P, but it's a local diffeomorphism around any point, not just around 0. That's the key thing. Okay? So when I say the exponential map is a local diffeomorphism, this is for any V in TPM. So you have to use that fact and use a bit of covering space theory, because M is given to be simply connected. Conclude that the exponential map is actually a covering, but then it has to be a diffeomorphism. Okay, it's a nice, it's a very nice theorem. Mixes a lot of things that you know in the proof, and the statement is superbly simple and beautiful. So, okay, any questions? Okay, so these are the first two theorems are things you'll see in the presentation. So, and then if you want, you can read up or ask your friends the question yourselves. So fine. So let's move on to the second part, which was, so this is already about sectional curvature one way or another, even in this theorem. So let us shift gears a little bit and talk about manifolds of constant sectional curvature. Okay? So as we had remarked earlier, constant sectional curvature manifolds have been an central object of study in the development of Riemannian geometry. Okay? And part of the reason being that they appear in a lot of different contexts, and the other reason being that they're also considerably simpler to analyze, because the curvature is the same, the sectional curvature is the same everywhere, which means the Riemann curvature tensor determined by the sectional curvature is also the same everywhere.
Sir,
So,
can you please go to the previous slide?
sure, yes.
Sir, here you make a statement that a crucial step to show that non-positive sectional curvature implies that exponential p is a local diffeomorphism for any p belonging to M. But then for any p belonging to M, exponential p indeed is a local diffeomorphism from a ball around origin to a ball around Q.
Yeah, so that's precisely what I said. So maybe you just missed that. So what I'm saying is exponential p is now a map on TPM because of completeness, right? So now, when you say a map is a local diffeomorphism, I mean a map is a local diffeomorphism around any point in the domain, not just around zero. So if I give you any vector v in TPM, I'm claiming that exponential exponential p around v is a local diffeomorphism, not just zero. Does that clarify?
Okay, sir.
So the
Yes, sir.
thing that we just proved using inverse function, which is the baby version, is that exponential p is a diffeomorphism only around zero. But in general, even if it's defined on TPM, this is never going to be a local diffeomorphism around all points. But that's the crucial thing, that for these kind of manifolds with these sectional curvature constraints, it's a local diffeomorphism. So it sort of starts looking like a covering space, so to speak, right? But then you have to actually bring in the pi 1 m is 0, do a bit of covering space theory to show that this exponential map is actually a covering. But once it's a covering, both are simply connected, it has to be essentially the identity map up to up to a diffeomorphism. So it's a diffeomorphism. That's basically the idea. Okay? Is that okay?
Okay, sir. Yes, sir.
Yeah. So yeah, so it's an important point. It's not to be confused with the old exponential being diffeomorphism, because that is at zero. This is at any v. Yes. Any other questions? Okay. So maybe I can move on here. Yeah. So as I was saying, that manifolds of constant sectional curvature are important, and these are related to classical non-Euclidean geometry, as you all know by now. So the geometry on the sphere, the geometry on the upper half plane, and the flat geometry, right? And so oftentimes people use the expression spaces of constant curvature. And whenever somebody says spaces of constant curvature or constant curvature, as I mentioned at the very outset, they mean constant sectional curvature, okay? So if they mean constant Ricci or constant scalar curvature, they'll precisely mention those two words. Otherwise, constant curvature means Riemannian manifolds of constant sectional curvature. And we are going to use this term for the subsequent slides. Okay, so there's one important property, because locally they are basically isometric. So there's a large number of local isometries, meaning if I give you 2 points P and Q in a manifold like this, you can find suitable neighborhoods U and V around P and Q such that U is isometric to V. This is a lemma that is proved in Locarno. It's not a hard lemma to prove, simply because of the sectional curvature restrictions. You can choose coordinates and apply transformations to show that given 2 points, there are local neighborhoods U and V, so that U is isometric to V, and U is a neighborhood of P, V is a neighborhood of Q. So there's a lot of local isometries, which is nice. I mean, this is not true for a random manifold, for the simple reason that just imagine you take a sphere, like, imagine a metallic ball, which is a sphere, and then hammer the sphere in all possible ways on the surface, but hammer with different force. So the sphere is now going to look like a big golf ball, which has dents of differing depth, right? So I mean, I don't have a picture for this. Just imagine this in your mind. Take a steel ball and then just hammer at various points of the surface with different forces, so that you create dents on the ball with different depths. So that is still a Riemannian manifold, but this is typically not going to have a large number of local isometries, simply because the curvature at different dents are different, right? So you cannot expect that given any 2 points, there's a local isometry from P to Q, simply because the scalar curvature at P might be entirely different from the scalar curvature at Q. and an isometry preserves curvature. So in general, for a generic manifold, you do not expect these things, but these manifolds, they have these nice properties. They're also related to symmetric spaces, for those of you have heard of that term or have seen some examples, but that's just for reference. Okay. So yeah, so let's get on with it. So let Mg be a Riemannian manifold. Let's make a few observations along the way before we state the main theorem. So the first observation is, and this is actually a good exercise. I didn't want to highlight this in red, but this is an exercise all of you should go back and do, because this is a good contender for a question that could be asked. Okay. And I'm not saying this because this will be asked, but this is the type of questions that you should know how to answer. So if you compare the curvature for the metric G and the scaled metric GC, where C is a positive constant. So you take the metric G and the new metric is C times G. So then one can check that the sectional curvature satisfy this reverse relation, that the sectional curvature function for the metric GC is 1 over C times the sectional curvature function for the metric G. And a pictorial visualization of this could be, take a sphere of radius 1 with the usual metric, the curvature is 1, scale this by 2, scale the metric by 2, and then one can show that the sectional curvature of the sphere with the scale metric will simply become half. Okay. That's because the original unit vectors now become 2. So if you calculate the sectional curvature, you have to scale by half. Okay. So it has this relation. Okay. So in other words, whenever we are dealing with spaces of constant curvature, you can always rescale the metric so that the new metric has constant sectional curvature 1. Right? Because if my sectional curvature is k, I basically rescale it by absolute k so that my new sectional curvature becomes either 1, 0, or minus 1. Okay? So that's the point, that we'll only be focusing on manifolds of constant sectional curvature or manifolds of constant curvature as we introduced. And we are going to assume that these numbers are either minus 1, 0, or 1. And that's simply by rescaling the metric, you can arrange them to be either 1 or 0 or minus 1. Okay. So is that okay? So we're going to assume that from now on, that whenever we talk about constant curvature spaces, these are of constant curvature minus 1, 0, or 1. Yeah, so k is equal to minus 0 or 1. All right. Any questions? Okay, so there's one final remark before we state the theorem. And I just talked about this, that an isometry preserves curvature, because an isometry, remember, is a diffeomorphism which is a linear isometry at the level of tangent spaces. And because it preserves the metric, it preserves all the various things that you can do with the metric, taking derivatives and so on. So it preserves sectional curvature. The converse is, however, not true. Okay? You can have a diffeomorphism between M and N, which preserves the curvature, but it's not an isometry. Okay? So a diffeomorphism preserving curvature is not an isometry. And I mean, there's an explicit picture of this in Dokarma as well if you want to look it up. But since it's going to take me astray, I'm not going to discuss this example, but there are examples. So, and we will see a lot of discussion on isometries of Riemannian manifolds. One of them is going to be Abhigyan's presentation, where he's going to talk about isometry of Mg, a very beautiful and classical theorem of Myers and Steenrod. And then Pallav is also going to talk essentially about isometries of the upper half plane. So these two things are related to that. Okay. So if there are no questions, let me state the theorem. Okay. So remember what we are trying to do here. We are trying to ask whether there's a characterization of spaces of constant curvature which are minus 1, 0, or 1. Okay. And we already know the answer for in dimension 2. We have seen that in dimension 2, R2 is flat, meaning its curvature is 0. S2 is the manifold of curvature 1, sectional curvature 1. And I'm writing this with this S because this is my notation for S with the Euclidean metric, not the topological S2. Okay? And H2 is, of course, the upper half plane, which is either the upper half plane with the metric dx square plus dy square by y square, or the Poincare disk with the usual metric. They are two different models of the same hyperbolic space. Okay? And that has constant sectional curvature -1, or constant Gaussian curvature -1. Yeah. So R2 corresponds to 0, S2 corresponds to 1, and H2 corresponds to -1, the three sort of classical geometries. Okay? And these three examples also happen to be simply connected and complete. Okay? So one can ask whether these are true in higher dimensions, whether the analogous models hold in higher dimensions. Well, obviously, in the Rn case, we know it does. Take Rn with the Euclidean metric. That is complete. It is simply connected, and it has the Riemannian curvature is 0. So all the curvature, sectional, Ricci, everything is 0. Okay. What about Sn? Well, Sn is the same thing. Think of Sn as the unit sphere in Rn plus 1 with the round metric induced from the Euclidean metric. So there's a G Euclidean metric on Rn plus 1 that induces a metric on Sn. I'm calling it the round metric. And that has sectional curvature 1. And this was computed in the class, and I think it was also assigned to Ulian or maybe somebody in one of these exams. So anyway, so this is the model for curvature 1. What about -1? Well, there's a similar model for the hyperbolic space instead of the plane. So this is Hn inside Rn plus 1 equipped with the hyperbolic metric. It's a metric which has constant sectional curvature -1. So you might ask, what is a model for Hn? Because we know what H2 is. What about H3, H4, and so on? Well, there are several models for the hyperbolic space. One model could be you simply keep taking the upper half spaces, take the same metric, you take the standard metric, divide by xn square. Like in the case of H2, what did we do? We took dx square plus dy square, we divided that by y square. You can do the same thing here, dx1 square up to dxn plus 1 square divided by xn plus 1 square. So that's the upper half space model. There's a ball model corresponding to the disk model, and then there's a hyperboloid model, which is probably the model which is more familiar to the physicists, because you have these Lorentzian group of isometries and so on. So there are several models for the hyperbolic space. They're all models of a complete simply connected manifold with constant curvature -1, constant sectional curvature -1. Okay? So here's the theorem. The theorem says you start with any complete Riemannian manifold with constant sectional curvature k, which is either -1, 0, or 1. Okay. So then you can talk about the universal cover of a manifold, because a manifold is semi-locally simply connected. If you recall whatever that thing is, it is true in the case of manifolds. Every manifold has a universal cover. Look at the universal cover M tilde, and it has a metric because you can take the metric on M and induce a metric on M tilde, right? We did this in the class. So with this covering metric, M tilde is isometric. So remember, I'm not saying it's diffeomorphic, I'm saying it's isometric, meaning it is identically the same as Hn, Rn, or Sn with the corresponding metric that we see up here. Hn with the hyperbolic metric, Rn with the Euclidean or flat metric, Sn with the round metric. So this is the statement that for any complete Riemannian manifold, its universal cover is as a Riemannian manifold, Hn, Rn, or Sn. Okay. So any questions or comments? Okay, so so these things have another name. So complete manifolds which have constant sectional curvature, they are so I mean, they make their appearance so frequently in so many different places that they have a name. They're called space forms, because these are your like three basic models for the space or geometries, and then you want completeness for various reasons. So for instance, if you want to ask what is a space form in even dimension, it turns out this is not an obvious fact, it's a theorem, but if you want a space form, that means you're asking for what are all complete manifolds with constant sectional curvature in even dimension and with sectional curvature 1. So you're looking for all manifolds M of dimension 2n which is complete, and the sectional curvature is equal to 1. And it turns out that the only such manifolds are SN or RPN. It's very restrictive simply because, as you see, whatever your manifold is, it has to be covered by Sn because the constant curvature is 1, right? Because of the theorem. But then you're asking what are the manifolds which can be covered by Sn? Well, that means whatever the fundamental group of this manifold is, that has to act as deck transformations on Sn. And we know that there are several sort of spaces that can happen. So in S3, of course, there are lots of different actions, but the typical space which has a pi1 and the pi1 acts on Sn is the antipodal identification on Sn, and that gives rise to RPN. And it turns out that with this constant sectional curvature assumption that it's only these two, Sn or RPN. So RPN can also be given a sectional curvature equal to 1 metric simply by using the isometries of Sn and the fact that the antipodal map is an isometry. If you quotient out Sn by the antipodal map, that induces a metric on RPN, which has the same curvature properties. Okay. So yeah, so this is a nice classification, and you will see a version of this for n equal to 2 in Sandeep's talk, where he's going to talk about what can happen for Riemannian surfaces or a Riemann surface. And it turns out for a Riemann surface of genus at least 2, they can be covered by the upper half plane. And because the upper half plane has this constant curvature -1 metric, it will actually, with some work, you can show that that will induce a constant curvature -1 metric on any surface of genus at least 2. So that's what Sandeep is going to talk about. Okay? So, and it has some really nice pictures, and there's a whole bunch of geometric group theory, dynamics, and things like that enter into the picture. It's a really deep and fascinating subject. So anyway, so that's basically this. So now I want to switch gears a little bit and talk about the two other sections. One is how does it relate to topology, meaning how does it relate to fundamental group and other topological invariants. And the last one is this section on sphere theorems. Okay. So before I move on, any questions or comments? Okay, so we start here. Yeah. So as we saw in this previous theorem, so it's connected. So in the previous theorem, what does it tell you? It says that if you choose, yeah. So it just says that if you choose a manifold. So let's go back one more slide, right? So let's even go back. So we don't even need this. Let's go back to Hadamard-Cartan theorem. Just look at this. It says if you have a complete Riemannian manifold which is simply connected, then it's diffeomorphic to Rn. And if it's not simply connected, but if it still has the same curvature constraints, then by this theorem it will turn out that it's covered by Rn. Okay, so it's a combination of these two theorems. I didn't state it exactly here, but I probably should have in hindsight. So it turns out for negatively curved manifolds, all the topological information lies in pi1, because for a negatively curved manifold, its universal cover is homeomorphic to Rn. Okay? That's a variant of the Hadamard-Cartan theorem, because Hadamard-Cartan only talks about simply connected manifolds, but you can rework that and show that any such manifolds with negative sectional curvature is covered by M tilde, but M tilde is Rn. So it's Rn, which means if you want to look at topological information of such a manifold, what do you mean by topological information? Well, typically one means the basic topological invariants, which are the fundamental group, which is pi1, or the higher homotopy groups. So for those of you who may have heard of it, fine. For those who haven't, there are analogs of pi1 in higher dimensions called higher homotopy groups. And what are they? Like pi1 is the set of all equivalence classes of maps from S1 to M, fixing base points. Pi 2, pi 3, so on, or pi k in general is going to be the set of equivalence classes of maps from a k sphere to your M, fixing base point. So you look at maps from Sk to M, sending the north pole to the point P, and you say that two such maps are equivalent if there's a one parameter family of base maps joining F to G. It's the same relation. Okay. So if you introduce this relation, it turns out that the equivalence classes of such based maps from the K sphere to M turns out to be a group, and it's called pi k of M, or the kth homotopy group of M, based at the point P. Okay, so pi 1 is just the equivalence classes of base loops, and you concatenate loops. Similarly, you can concatenate two spheres and so on. So if you're given a sphere, you can just collapse the equator, that becomes two spheres, and that's how you concatenate. So that's a separate story, but there's this whole theory out there that you can calculate or ask for calculating pi 2, pi 3, and so on. The only difference is that the higher homotopy groups are all abelian. So I'll make that remark later on as well, but keep that in mind. It's a drastic departure from pi 1. Typically, pi 1 is not abelian, as you might have observed in the algebraic topology course. But pi 2, pi 3 onwards, because it has more room for moving things around, they are abelian. Okay. However, these are notoriously hard to calculate. Okay? So even for spheres, even for S2, for example, we don't know what are all the pi k's. We know certain things about certain groups appearing in ranges and so on, but there's no general answer to what is the pi k of a given space. Okay? So those are hard to compute, but those are invariants, and in fact, very crucial and important invariants of space. So because for a negatively curved manifold, the universal cover M tilde is diffeomorphic to Rn, the higher homotopy groups of M are all going to turn out to be zero, because the higher homotopy groups turn out to be independent of which cover you choose. So if you want to calculate pi 2 of a space, you can choose its universal cover and calculate pi 2 of the universal cover. They'll be isomorphic. Okay? That is not true for pi 1, but for pi 2 onwards, the universal cover and the space, they have the same pi 2, pi 3, pi 4, and so on. So that implies that if I wanted to calculate this object, higher homotopy group pi k of M, it suffices to compute pi k of M tilde, but M tilde is Rn, and Rn is contractible. So pi k of Rn is 0, because every mapping of a sphere into Rn can be contracted to the constant mapping, because Rn is convex, right? So that's basically, so it took me a while to explain this, but that's what I mean. So for negatively curved manifolds, all the basic topological information is only there in pi 1. There's no other higher information. Okay? So which in turn implies that maybe pi 1 is really very, very rich, and indeed it is. And there's a whole bunch of things that one can talk about, which leads to work by Milner, work by Gromov, work by Margulis, all great mathematicians. But I'll stick to what's relevant to our framework. Okay. So are there any questions, even vague or whatever, about what I just said? So I think most of you may not have seen higher homotopy groups, but hopefully the idea was clear that there's analogs of pi 1, and those are abelian, and you can compute them by computing them at the universal cover. But for these manifolds, the universal cover is Rn, so the only non-trivial topological data is hidden in pi 1. Okay. So any questions or comments? Okay, so let me state this theorem. This is also there in Locarno. So this is Priceman's theorem. So we'll see him appear again a bit later. So this is saying that if you choose a compact Riemannian manifold with sectional curvature k less than 0, so this is strictly less than 0. So sometimes this strictly less than 0 and less than or equal to are very, very important in Riemannian geometry, because depending on the strict inequality or the non-strict inequality, things can change drastically. Okay. So anyway, so you choose a compact Riemannian manifold with sectional curvature k less than 0. So for instance, if you want a concrete example of such a manifold, I'll again refer you to what I just said regarding the presentation that will be done by Sandeep, I presume, which is choose a Riemann surface of genus 2, meaning choose one of these spheres and attach two handles. Okay? So it's like a kettlebell, but sort of with two handles, right? If you go to the gym and do workouts and stuff. So choose a Riemann surface of genus 2, then that it turns out that you can put a Riemannian metric there so that it has sectional curvature is equal to -1. It's clearly compact. So, and in general, you can choose any genus G Riemann surface G is at least 2, and it's compact and it satisfies this condition. So you can apply this theorem to those examples if you want to have a concrete example at your fingertips. So the theorem says if let H be any non-trivial abelian subgroup of pi 1m. Okay, so pi 1m is a group. It is typically non-abelian, but assume that H is a non-trivial abelian subgroup. Then H has to be Z. That's what this is saying. So H is infinite cyclic. It cannot be anything else. It cannot be torsion. It cannot be Z mod 2. It cannot be Z cross Z. It cannot be anything else. It has to be Z. So, I mean, of course, there may be no abelian subgroups at all, in which case pi 1 might be strictly non-abelian. That is completely fine. But if there's a non-trivial, meaning non-identity abelian subgroup, it has to be infinite cyclic. So this is a, it's a very nice statement, at least on the face of it, just by assuming constraints on the sectional curvature, which goes to show that imposing constraints on the sectional curvature sometimes is quite a it's quite a constraint. Okay, so I'll not get into the proof, but a key ingredient in the proof is an analysis of geodesic triangles in negatively curved spaces. So when you have a negatively curved space, even let's say the hyperbolic plane, if you want a triangle there, you want a geodesic triangle, right? So which means you are looking for the analog of the standard triangle on the flat plane inside the upper half plane, which means it should be 3 vertices, and the 3 vertices should be joined by 3 geodesics, A to B, B to C, C to A. So if you want to think of how such a triangle looks like in the upper half plane, it's a good exercise to go back and think about. So those are the kind of triangles we want to analyze in this manifold M, which is now not constant sectional curvature, but negatively curved. Okay? So if you do this analysis, compare angles, compare areas, and so on. So that's one of the ingredients in the proof. Okay? So a particular implication of this theorem is that if you want to say, okay, is this useful in ruling out certain manifolds from admitting negatively curved metrics? Because oftentimes you are looking for manifolds which admit certain metrics or they do not. So for instance, if you ask, can the M torus, meaning take S1 cross S1 cross S1, M copies of them. So S1 cross S1, if you take the two torus is usually just S1 cross the usual torus. The 3 torus is usually going to be S1 cross S1 cross S1. It's a 3-dimensional manifold, and so on. So if you look at this TM, it does not admit a metric of negative curvature or negative sectional curvature. So I'll pause here for a moment and I'll let everybody think for a minute or two. Can you say why the theorem implies that this cannot admit a metric of negative curvature provided M is at least 2? So you have to recall some of the things from algebraic topology a little bit. So you can argue by contradiction. If it did, what would happen? So if it did, then
Sir,
yes. Yeah.
sir, that fundamental group of TM should be that the fundamental group of S1 cross fundamental group of S1. That means that Z cross Z cross Z, and Z cross Z is a abelian subgroup of that group, but not infinite cyclic.
Right. So if you have M to be at least 2, then if you look at the pi 1 of this TM, pi 1 of TM is simply the product of the pi 1, which is Z cross Z cross Z, so it's Z to the M, right? And Z to the M always has a copy of Z cross Z, for example, if M is at least 2. But the theorem says that if H is any non-trivial abelian subgroup, H has to be isomorphic to Z, and clearly Z cross Z is not isomorphic to Z. Right? So this, I mean, so TM cannot admit such a metric, for example. This is a very simple example, but you can with some effort you can work out some slightly more non-trivial examples too. If you have to know a little bit about the fundamental group its abelian subgroups, and then you can rule out certain kinds of curvature on that manifold. Okay. So is that okay with everyone? Okay. So yeah, so in fact, there's a modification of this or a variant of this which was also proved by Priceman. So he showed that with the same assumptions above, meaning compact Riemannian manifold with sectional curvature k less than 0, you can show that pi1m is actually not abelian. Okay? So that doesn't mean that it cannot have an abelian subgroup. Okay, so make sure that you understand the distinction. So pi1 of m is not abelian. That simply means it's not abelian. It could have abelian summands. Okay. So, okay. So there's actually, so I guess these were refined later on by Byers, where he replaced H with, I think, non-trivial solvable subgroup and so on. But you can read up on the history of that in Ducharme and other books. But this is, I think, a nice statement to have, a nice clean statement. Okay? So it's combining topology, algebraic topology, and Riemannian geometry in a very nice way. Okay, any questions? Okay, so let me state things without curvature restrictions. So now we just change our viewpoint a little bit and we consider Riemannian manifolds with no curvature restriction, negative or positive. Just Riemannian manifolds, back to the basics. And we want to talk about closed geodesics. Okay, why are we trying to talk about closed geodesics? Well, we just talked about pi1. And what about pi1? Well, the elements of pi1 are given by loops. Loops are nothing but closed curves. So meaning they are maps from S1 to your space M, which is smooth or continuous as the case may be. And typically for pi1, these are base loops. Okay? And the reason why one would like to analyze closed geodesics is because closed geodesics are one of the important objects in mathematics, physics all over the place, because it appears in Morse theory, it appears in dynamics, it appears in calculus of variations, it appears in as critical points of the energy function, and so it just appears all over the in stability phenomena and so on. So closed geodesics are very important for various reasons. So you'd want to analyze closed geodesics and see what connections they have with closed loops or loops. Okay? Because not any loop is going to be a closed geodesic. It's simply a closed curve, and geodesics are somewhat special. So a natural question is the following. So if I give you a loop in M, meaning it's a map from S1 to M, can we freely perturb it or homotop this so that we obtain a closed geodesic? So I hope you should have a picture of this in mind. You have your M and then there's it's like a rubber band or something, which could be self-intersecting and knotted and so on, lying in the space, and you're trying to perturb this thing or homotop this thing so that at t equal to 1, the perturbed version is actually a geodesic. So whether it exists or not, you can still ask this question, right? And typically we're interested in non-trivial elements of pi1, because if I give you the trivial element of pi1 that corresponds to the equivalence class of the constant loop, but the constant loop is also a geodesic. It's a constant geodesic. Right? So the constant geodesics are also geodesics because it's a constant map. So we are interested in non-trivial elements of pi1, meaning we're interested in geodesics which cannot be shrunk to a point. Okay? So, okay. So having said that, so we'll be concerned with a smooth loop gamma, which is not homotopic to a constant loop. Okay? Because if a smooth loop gamma is homotopic to a constant loop, then you can choose the constant loop to be the geodesic. And then obviously gamma can be perturbed to the constant geodesic. So that's the easiest case which we rule out straight away. So here's the theorem of Cartan, and it starts with M being a compact Riemannian manifold. Okay? And I'll make a remark later saying why compactness is essential. So let M be a compact Riemannian manifold. If gamma is a closed loop, which is not freely homotopic to a constant loop, then there exists a closed geodesic gamma tilde which is freely homotopic to gamma. So I hope the statement is clear. We start with a closed loop. So I shouldn't have said closed loop. A loop is automatically closed. But if you start with a loop which is not homotopic to the constant loop, then I can find a closed geodesic gamma tilde which is homotopic to gamma. I hope the statement is clear. Are there any questions regarding the statement or any clarifications that you have?
The freely homotopic means?
Yeah, okay, good. So I was hoping somebody would ask this. See, I'm mentioning the word freely homotopic because in algebraic topology, you have seen the notion of two loops being homotopic, and usually that means two loops being based homotopic, right? So if you say I have a loop, that means you have a map from S1 to M. But S1 already comes with a chosen base point, which is 1. So when you say gamma and eta as loops are homotopic, usually you mean that gamma of 1 is x0, eta of 1 is x0, and there's a one parameter family of loops h of t, so that h of t comma 1 is also x0 at all times. So these are homotopies preserving the base point at all times. The freely homotopic means that this h of t at 1 is x0 is not required anymore. So these are loops which are homotopic to each other as loops, but the base point condition is not there. Okay. So if you take a loop and you start rotating that loop, that's a homotopy of the loop to itself, but it's not a based homotopy because the base point changes if you start rotating the loop. Right? So that's what I mean by freely homotopy. So there are several reasons to ask why you need freely homotopic. Well, one would be that given a point, if given the base point, there may not be any closed geodesic passing through that base point because the manifold is just a generic manifold. Okay? So freely homotopic is really the right notion that you're looking for two loops being homotopic, but they're not based homotopic. That's all I mean. Okay. So any other questions? Okay, so let me.
Can you repeat why do we need freely homotopic?
So why do we? So why means this is probably not a formal reasoning, but why is because if you insist on a closed geodesic gamma tilde, which is based homotopic to gamma, then that in particular means what? It means that you are first of all assuming that there is a closed geodesic gamma tilde which passes through the base point x0, right? I mean, whether or not it is homotopic to gamma is irrelevant. That there is at least a closed geodesic, a non-trivial closed geodesic, because it's homotopic to gamma, and gamma is not homotopic to a constant. So you are expecting a non-trivial closed geodesic passing or initialized at x0. But because the manifold is a generic manifold, if I give you a point, you cannot expect that there is a closed geodesic passing through that point. I mean, there are geodesics passing through that point, and M being compact ensures that it's complete, which means that the geodesic passing through that point will exist for all times, but that geodesic will not be a closed geodesic. It will typically be a path which just keeps going on either end. Okay. So in general, if I give you a point, you cannot expect that there's a closed geodesic passing through that point for a generic metric on a Riemannian manifold.
So when we mean closed geodesic, we do not include piecewise geodesic.
No, this is a smooth curve, which is a geodesic, and closed means that it's essentially like one periodic. So it's a think of it this way. You can either think of it as a smooth map from S1 to M, which satisfies the geodesic equation, or you can think of it as a smooth map from R to M, which is 2 pi periodic and a geodesic. Either one, they're equivalent. So a closed geodesic would mean, like in the case of a sphere, if you think of the great circle, a closed geodesic is simply going to be one single iteration of the great circle. But you can also think of that as a great circle going over and over and over itself, and that's a map from R to M. If you want to think of it as a map from R to M, then it's a 2 pi periodic geodesic, right? or some C periodic geodesic, basically. So that's what a closed geodesic is. So a typical geodesic which is not closed is going to be, so yeah, so that was the question that I was going to get to. So if I think of R2, for example, R2 is of course not compact, but does R2 have any closed geodesics? And this is a question that all of you should be able to think and answer. R2 has lots of geodesics because it's complete. So does R2 have any closed geodesics? The closed means that
No, because all are straight
yeah,
lines.
they're all straight lines. So if it shoots off in one direction, it will shoot off in the other direction. You can never get periodicity because it just keeps, it's a monotone thing, right? So similarly, if you look at the hyperbolic plane, for example, the upper half plane, one can show that the upper half plane has no closed geodesics for the same reason, that it keeps going to infinity. Okay? However, the sphere has closed geodesics, right? The great circles. And the sphere is the only one among the three examples that I just talked about, which is compact. So compactness is essential. Okay, you cannot do this in non-compact setting for the most part. Okay, and so, and the other point being that if I even if I give you a general manifold, compact or not, if I give you a point, there may not be a closed geodesic passing through that point. There may be a geodesic, but that may not close up. That's one issue. So that's the point, okay? That you don't insist on based homotopic, but freely homotopic. So your base point is allowed to change. Okay, any other questions or clarifications? Okay, good. So yeah, so this is actually something that is very close to my heart, and I would really want to talk more about this, but that would take me away from what I want to talk about today. So I'll not make that digression. But the thing that you should note is that Cartan's theorem, or at least the proof, if you go back and read Ducarmo or even one of the earlier texts, I think Burkhoff probably had more or less a similar idea for proving this. It is related to curve shortening process and so on. That the proof does not work for simply connected manifolds, because for a simply connected manifold, no matter what loop you choose, any loop is going to be homotopic to the constant loop, freely or even based homotopy, because it's simply connected. That's what it means to be simply connected. Pi 1 is 0, which means every loop is in the equivalence class of the constant loop. So his proof or even the statement will not work for simply connected manifolds, right? So the question is, what do we do then? So can we still prove that there exists some non-trivial geodesic even when the manifold is simply connected? That's a very natural question to ask, right? So we know that for spheres, for example, there are non-trivial geodesics. Namely, any of the great circle is a geodesic. However, S2 is simply connected. Okay. So what should we do then? Well, it turns out there's a fix, and the answer is in the affirmative, that the modified version of Cartan's theorem is true even when the manifold is simply connected. Okay. So I hope the simple connectivity assumption is clarified now. I mean, what was not assumed in Cartan, and if you assume, you need a new way to prove things. Okay. So, okay, let me move on. Yeah, so there's this following beautiful result by Lustenich and Fett, who proved the following. So let M be a compact and simply connected Riemannian manifold. Then there is at least one, so I missed a one. Okay? There is at least one non-trivial closed geodesic in M. So by non-trivial here I mean that this is a geodesic which is not the constant geodesic. Okay? So on the sphere, for example, the constant maps are geodesics, the great circles are geodesics, and these are all. So what we mean are geodesics like the great circle. So they are not the trivial maps, constant maps, and they're geodesics. So there is at least one such. That's what they prove. And this is for M with any Riemannian metric. Okay, as we will see that the Riemannian metric is very crucial. If you change the Riemannian metric, the geodesics might all of a sudden, the number of geodesics might all of a sudden, uh, shrink. The number of closed geodesics. Okay. So if you want to read a modern sort of proof of this theorem, you should either read one of Bott's survey papers, or you can read the exposition by Milner, the following Bott, from his Morse theory book, where he explains how Morse theory can be used to give a very elegant proof of this result. Okay? It's highly recommended. In fact, that is the source where I probably learned from, and most of the people, the modern sort of mathematicians learn from. That the the Morse theoretic proof due to Bott of this theorem. So it's true that even if the manifold is simply connected, there are lots of non-trivial closed geodesics. In fact, there's at least one. So there's a whole bunch of literature on this. So this is related to loop spaces, closed geodesic problem. There are conjectures of Gromov and so on, and which leads to a lot of deep mathematics. But I wish there was time, and maybe in some later lectures or courses, I'll get the chance to talk about that. But let me end this section with a famous conjecture of Bott, which is mildly related because it's related in the sense that it's the same Bott, Raoul Bott, but it's not related in this sense of existence of closed geodesics. Okay, so yeah. So speaking of Bott, I cannot help resist but share this quote with you. So he was a very charming person to speak to and a wonderful conversationalist, and he was an excellent orator and lecturer as well. So he could sort of grab you in the lecture and sort of immerse you in whatever you're saying. And one of his famous quotes was the following: "Every mathematician has a weapon. Mine is Morse theory." And if you go back and read what Bott has done and how he used Morse theory, I mean, you'd really see why he said what he said. Okay. So conjecture due to Raoul Bott is the following: that you choose a compact, simply connected, non-negatively curved Riemannian manifold. So forget the last two terms. So now we are switching gears. We are saying, okay, what happens to the non-negatively curved setting? Because so far we have talked about the negatively curved setting, and we saw that pi 1 was essentially the only topological information. So he conjectures that if you take a compact, simply connected, non-negatively curved Riemannian manifold, meaning that the sectional curvature is bigger than or equal to 0, then such a manifold is rationally elliptic. So I have to remind you, or I have to maybe define for you, what is rationally elliptic, because this is a term which probably most of you haven't seen. And this has, as far as I know, this has nothing to do with elliptic PDEs, but it's elliptic because of some finiteness condition. Okay, because elliptic things are usually compact and finite and so on. That's probably the name. At least that's my guess. Okay, so remember I was talking about the higher homotopy groups for a little while, pi 2, pi 3, and so on. And I mentioned that these higher homotopy groups are abelian. Pi 1 is not abelian, but pi 2, pi 3, they're abelian. So whenever it's an abelian group is also a Z module. All of you should remember this from your rings and modules, that an abelian group is nothing but a Z module. So if you have a Z module, you can tensor that with Q over Z. So this tensor here is happening over Z. Okay. So this is the abelian groups pi j of x, thought of as a Z module, tensor with Q over Z. So this is now, this is now going to be a Q vector space because I've tensored with Q. So a space is called rationally elliptic if, when you rationalize the higher homotopy groups, meaning you tensor pi j of x with Q, these Q vector spaces are 0 for sufficiently large j, meaning after some capital N, all these higher homotopy groups tensor Q are 0. So is the definition okay? Or do some of you want me to sort of repeat this? So it might be a bit cryptic of a definition in the sense, why am I defining this all of a sudden? Well, there's a whole topic of rational homotopy theory where people study spaces, and it's a theorem that spaces are either rationally elliptic or rationally hyperbolic. And rationally hyperbolic is defined in an entirely different way. I'll not get into that, but rationally elliptic spaces are usually like far and few. They're not too many. A generic space is usually of the other kind, and very few spaces are of this kind. Okay? Because this puts severe restrictions on your higher homotopy groups. For example, if you take J to be 3 and if you take pi j of x tensor Q is 0, that means what? That means think of pi j as an abelian group. As an abelian group, it has some free parts, meaning z cross z cross z, and it has some torsion parts, right? So when you tensor this with Q, which part goes to 0? So if you have an abelian group, z cross z k copies plus some z mod n1z, z mod n2z, and so on. If you tensor this with q, which part vanishes? So this is like a basic algebra 3 question. Right? So this all of you should be able to say. So if you remember, z mod 2 cross, z mod 2 tensor q is 0. So the torsion part will vanish whenever you tensor with q, because q has no torsion. So this simply says that you look at the higher homotopy groups and you forget the torsion. Look at the free part, the free cycle, the free abelian part, and the free abelian part is basically 0 after a point, which essentially means that your space has higher homotopy groups which are torsion after a point. There's no z to the k in pi j. That's all this means, okay? So anyway, so rational elliptic spaces are generically rare, and what Bott's conjecture is suggesting is that if you're looking for compact simply connected non-negatively curved manifolds, then these are of this kind. So there's a topological characterization, okay? So if you want an example of rational elliptic spaces, I guess, so S2 is rational elliptic, for example, okay? So all the spheres are rational elliptic, but there are plenty of 4 manifolds which are not rational elliptic. So anyway, so if you want, we can talk about this after the thing ends, but this is, it's going to be a digression if I say more, but this is just the tip of the iceberg. So if you want to look it up, look up any text on rational homotopy theory. So that's what this conjecture says, and this is still open in its generality as of now. Okay, so now we're ready to move on to the last section, the sphere theorems. So any questions or comments before I move to the next section?
Sir, you were talking about Morse theory. So
Yes.
these have a lot of applications in gauge theory, right? The Morse theories.
It could see, I mean, Morse theory in general, it's basically a way of extracting topological information of a manifold by studying functions on the manifold. So Morse theory later on has been generalized in the context of symplectic geometry and topology and contact geometry and topology. And
Because I know that in certain gauge theory, the existence of sphalerons were proved by using tools from Morse theory.
no, that could happen. See, Morse theory in general is a very big tool, but what I'm saying is in symplectic geometry, for example, they have this technique called Morse floor theory or Morse floor techniques. And Morse floor techniques are things which also appear in supersymmetry and gauge theory, or at least appears in some of the works of Whitman, for example. So there is definitely some connection, but I don't know how explicitly one has used the other side and so on. But yeah, so these appear in symplectic geometry and topology, and that is probably the connection to supersymmetry or gauge theory or floor theory a la Witten. And that would be my guess if I were to start looking. So yes, I mean,
Okay.
so yeah, so Morse theory, so what I'm talking about here is a very nice application of the classical Morse theory, but the Morse theory in the modern formulation is quite general. And you can talk about Morse theory even in the infinite dimensional manifold setting, which is Morse-Smale theory, or even more generally, there's other things that one can talk about, and then there's the symplectic side of things, which relates more to physics. So yes, so they're all like various avatars of Morse theory. So this is more the classical version, which like Bott used to prove this theorem. Okay. Any other questions? Okay, so let me finally move on to the last thing. So as I said, there are too many beautiful and great results in this subject, so I couldn't simply mention all of them, but let me at least mention one. So, and you'll see this appear in almost any list of great results in Riemannian geometry. So it's called the sphere theorem. Let me state the theorem straight away. It's by Berger and so Marshall Berger and Wilhelm Klingenberg. So this was proved in around the 60s. The dates are all there in the first slide. You can go back and look it up. So it says that if M is a complete simply connected Riemannian manifold, N is for the dimension. So Again, it's complete, simply connected, it has a metric, and the sectional curvature takes values in this open closed interval 1, 4. It's crucial that 1 is open and 4 is closed. Okay. Then M is homomorphic to Sn. It's a very beautiful and strikingly simple statement, right? It just says that the sectional curvature, which is not necessarily a constant, takes values in this range, then M has to be homomorphic to the N sphere. Okay. So, so it is also often referred to as the quarter pinch theorem. And the reason is the following, because we saw that if I scale the metric by C, then the sectional curvatures get scaled by 1 over C, right? We saw that in one of the previous slides. If I scale my original metric G by 4, what happens to the sectional curvature? The sectional curvature gets scaled by 1/4, correct? Which means in my new rescaled metric, the sectional curvature takes values in open 1/4, 1 closed, right? And hence the quarter. So you're just saying that if the sectional curvature was constant 1, then we already know from Hadamard-Cartan theorem or one of these constant curvature theorems that M is diffeomorphic to Sn if K was identically 1. So now you're saying that it's not necessarily 1, but it can have some freedom of going all the way up to 1/4, but not equal to 1/4. So that's why the quarter pinching. But as long as it ranges in that interval, 1/4 to 1, it is still homomorphic to Sn. Okay? So hence the quarter pinch theorem. So you can replace 1/4 with 1/4 1 or C comma 4C, because you can rescale the metric and then the sectional curvature rescales inversely. Okay? So as we'll point out later on, the strict inequality on the left-hand side is necessary. If you replace this theorem with the statement taking values in closed 1/4, then it's not true that M is homomorphic to Sn. Okay? So are there any questions with this comment or the statement? And then I'll go into the remaining things. Any question regarding understanding the statement? I hope you take in what the statement is saying. Okay, so the short history is that Hoff had actually conjectured that a simply connected manifold with pinch, so this is called the pinching, right? Because you're saying it can go from 1 to 1/4. So how far can you, I mean, what would be the smallest that you can go from 1/4 and still prove the theorem? So Hoff actually had conjectured that a simply connected manifold with pinched sectional curvature is a sphere. Okay, meaning that the sectional curvature lies in some a comma 1. So in the early 50s, Rauch showed that with sectional curvature lying in 3/4 1, such manifolds are homomorphic. So yeah, there should be some. So just a second. Yeah, so I think this should be open, but anyway, I think even closed is fine. So Rauch actually showed that with sectional curvature lying in 3/4 1, such manifolds are homomorphic to spheres. So remember, if you choose a very small interval close to 1, 1 minus epsilon comma 1, chances are more that that manifold looks like a sphere because your sectional curvature is getting more and more closer to 1, the constant curvature 1, and then we can use the constant curvature theorem. So the question really was, what would be the optimal constant to put here? If you fix the right-hand side to be 1 by scaling, what would be the optimal constant to put here? And it turns out that 1/4 is indeed the optimal constant, and it's open. Okay, open 1/4. So Rauch had extended from 1 to 3/4, and then in the 1960s, both these gentlemen proved the above theorem. Okay? And this is optimal because you can take CPN, and I may have mentioned this in the class in one of the very first lectures, that CPN has a metric called the Fubini-Studi metric. I might have even written this down, but just take it and try it for CP2, for example. So with that metric, if you calculate, you'll see that CPN has sectional curvature which takes values between 1/4 and 1, and it takes the value 1/4 and 1, both of them. So it takes the entire closed interval 1/4 and 1. However, CPN is clearly not homomorphic to Sn, right? Because CPN has cohomology or homology in even dimensions. Sn has no homology in middle dimensions. So CPN is not homomorphic to Sn, okay, or like CPN is not homomorphic to S2n, but CPN has sectional curvatures taking values in closed 1/4 1 or closed 1 and 4. So this is an optimal number, the 1/4. So this is also called the quarter pinch theorem. Okay? So any questions regarding? So I mean, there might be some obvious questions which some of you are not asking. So here, after all of this Riemannian geometry, smoothness, curvature, we are concluding that M is homeomorphic to Sn. So you might ask, why did not we conclude that M is diffeomorphic to Sn, right? That would be a much stronger claim. Why is it only a topological identification? So the reason is actually deeper than you might think. It's not just because that this proof sort of fails or whatever. The reason is basically that there are spheres in higher dimensions which have smooth structures which are not diffeomorphic. And these are called exotic spheres. And this was a remarkable discovery due to John Milner, where he discovered that S7, the 7th sphere, has 28 distinct smooth structures, meaning that you can define 28 distinct atlases on S7, and each one of them would give you a smooth structure on S7, but the identity map from S7 to S7, from one atlas to another, is not a smooth map. So the identity map is not a diffeomorphism for the two underlying smooth structures. So this was remarkable because then people actually started looking for manifolds which the topological manifold is the same, but the smooth manifolds has two or more different smooth structures which are not diffeomorphic to each other. And such things exist. They definitely exist for spheres. That's, I think, the full analysis due to a paper due to Milner and Curvature called Smooth Structures on Spheres 1 or something. There's no part 2, but it's something along those lines. There's only one big famous, like paper by Curvature and Milner together. So that's that. So in high dimensions, just because you have a topological sphere, it does not mean that it's the standard smooth sphere. Okay? So the standard smooth sphere will mean the smooth structure that you obtain on Sn by thinking of it as a subset of Rn plus 1. But there are other structures which need not come from this embedding. Okay? So that's the reason. So just because you have a homeomorphism does not mean it becomes a diffeomorphism. So it's remarkable that the following result is true, and it's now known as the differentiable sphere theorem. It is due to Simon Brendel and Rick Shane. So this says that if Mn is a complete, simply connected Riemannian manifold with sectional curvatures taking values in open 1, closed 4. Actually, the assumption is slightly weaker, but let me not get there. I think this is good enough. Then M is diffeomorphic to Sn with the standard smooth structure. So M is the standard Sn. You don't get any of these exotic Sns. That's the theorem. So again, as in the last statement, this is a beautiful theorem with a clean, beautiful statement. And it's a generalization of the basic sphere theorem. Okay. So this was proved in 2007, which is recent in mathematical terms. So how do you prove this? Well, I haven't read this, so I am not anyway in a position to comment on how you prove this. But it turns out that they crucially use work done by Hamilton and some other people before them. And they also use Ricci flow in a very crucial way. So they use Ricci flow to show that this metric can be deformed using Ricci flow to a metric of constant curvature 1. And then because it's constant curvature 1, it has to be Sn with the standard smooth structure. So again, Ricci flow comes to the play, and you get a proof of the differentiable sphere theorem. So yeah, any questions regarding the statements or anything that you have in mind which connects to whatever we talked about today? We talked about a lot of things. Hopefully just go back and read through them like you read like a storybook or something. So it's more like a narrative, connecting several things along the way, hopefully highlighting for you that there are a lot of things which you can do with curvature, and a lot of things which, I mean, there's a lot of interplay between geometry and other things, and definitely in particular between geometry and topology, algebraic topology. So yeah, any question or comments or remarks? Anything that you want me to go back to? Okay, so if there are no other questions or comments, so then I'll stop here.